All right, guys, let's welcome you to lesson 2, which is going to be talking about half-lives. Now, this lesson is going to be longer, but what we're going to do is we're going to go through all the different types of half-life problems that you could see on a test or on a quiz or on another assessment that we might give to you this year. And we're going to go through those step by step. And then in your practice packet, all of your practice problems having to do with half-life are broken down based on what kind of problem they are. So let's first talk about what half-life is. Radioactive substances decay at a rate that is not dependent on temperature, pressure, or concentration. We've talked about temperature. Pressure is the force per unit area that the gas particles are pressing on something, and concentration is how much of the stuff do you have. The time it takes for half the atoms in a given sample to decay is what we call the half-life. So we do have samples that decay at a certain amount of time, and they vary from years all the way down to minutes, down to seconds, sometimes even days. So when you calculate half-life, you're looking at half of your sample has decayed, and that you have your radioactive element still left, and it will only be in 50% because half of it has decayed and become something new. After 2 half-lives, 25% or a fourth of your radioactive element is still present. So that means that 75% of your active element has decayed, leaving you just 25% or 1/4 that has still not decayed. After 3 half-lives, 12.5 or 1/8 of your radioactive element is still present, and this continues forever. The number will never reach 0 because there is no such thing as 0 point all zeros. So this number will still continue and go on and on and on and on and on. The half-lives are listed on table N for the different radioactive isotopes that we know about. So here we have your nuclides. Here we have your half-lives. So based on these nuclides, we know that this is the amount of time it takes for half of the sample to decay. We know how they decay, alpha, beta, or positron. And then this is what the name of those isotopes are. This is in your reference packet on table N. So the shorter the half-life of an isotope, the less stable it is. So if something decays in 20-something seconds or in seconds or in minutes, that means it's very unstable. The longer the half-life something has, that means it's more stable. So if it takes years or days for something to decay, that means that it is a more stable isotope that will eventually, as time goes by, will decay. So let's look at a bunch of different examples of half-life problems. This is where you need to pay attention, and I'm going to go as slow as possible. So this might take a while. So this video is going to be a little bit longer than normal. So let's look if you are being asked to calculate the amount remaining. So the question is, if a sample of iodine 131 has an original mass of 52 grams, what mass will remain after 40 days? So this problem is a two-step problem. So the first thing you're going to do is you're going to look up the half-life of iodine 131 in your reference packet, table N. The half-life of iodine 131 is 8.01 days. Now what you need to do is you need to look. You know that 40 days have passed, and you know that one half-life for this isotope is 8.021 days. So you need to determine how many half-lives have passed by dividing the time passed by the half-life. So we're going to take 40 divided by 8.5, 8.021, excuse me, and that means that there were 5 half-life periods that have gone by. So what we're going to do now is we know that we need to cut this 52 grams, our original mass, in half 5 times. So we're going to start off with 52. When we cut that in half, we get 26. When we cut that in half again, we get 13. When we cut that in half again, we get 6.5. When we cut that in half again, we get 3.25. And when we cut that in half again, we get 1.63. So we cut that in half 1, 2, 3, 4, 5 times. So if I wanted to know the amount of mass remaining if 40 days passed, I would say that after 40 days, 1.63 grams of iodine 131 is left. This is one example. This is how you would calculate, and these are the notes you should go to when you look in your practice and you have to calculate the amount remaining of a substance after it decays. Let's look at another example. What if we were asked what fraction of the original sample was left? So now we're not going to look at an actual number. We're going to look at a fraction. So 1/2, 1/4, 1/8, 1/16, something along those lines. So again, the first thing you're going to do is if you know how much time has passed, you can use table N to look up what the half-life is of the radioactive isotope. Again, we're looking at iodine 131, so our half-life is 8.02 days. So we're going to divide our total time by the half-life. So 40 divided by 8.021 is 5 half-life periods. Since we want to know the fraction remaining, we're going to assume that we start off with 1. And we're going to cut that in half, the amount of half-lives you calculated, and we're going to keep that in a fractional form. So that means that we're going to start off with 1, we're going to cut it in half, which is a half, cut a half in half, which is a fourth in half, which is an eighth in half, which is the 16th, and a 16th in half was 1/32. So again, we cut this in half 1, 2, 3, 4, 5 times because we had to cut it in half 5 times because in 40 days we underwent 5 half-lives. And so we would say after 40 days, 1/32 of the original iodine 131 is left. What if we were asked to look at the number of half-lives? So if I were asked, how many half-life periods will it take for 50 grams of technetium-99 to decay to 6.25 grams? So now what we would do is we'd find the number of half-lives by having the original mass until you get the final mass. So we know we're starting off with 50 grams. Well, how many times do we have to cut that in half until we get 6.25? So we start off with 50 cut in half is 25. 25 cut in half is 12.5. 12.5 cut in half is 6.25. How many times do we cut that in half? That will tell us how many half-lives we have. So that's 1, 2, and 3. So we cut that in half 3 times, which means that it took us 3 half-lives for technetium-99 to decay from 50 grams to 6.25 grams. What about another problem? What if the problem asked for you to calculate half-life? Well, this is how you would set it up. This problem says, what is the half-life of 500 gram sample of a radioactive element if 125 grams remain after 20 hours? So this is a 2-step problem. So the first thing you would need to do is find the number of half-lives by having the original mass until you got your final mass. So we're starting off with 500 grams, and I want to know how many times do we have to cut that in half to get to 125. Well, the first time we cut 500 in half, we get 250. That's not 125, so we have to cut it in half again. So we cut 250 in half, and we get 125. That is how much of our radioactive element remained after the 20 hours. So it took us 2 half-lives. We had to cut that in half twice in order to figure that out. Now, if we know the total time that it took was 20 hours, and in that 20 hours, 2 half-lives went by, we could take 20 hours divided by 2, and so we would find that 1 half-life is about 10 hours. What if you were asked to calculate the original mass? So this means you're working backwards. So now we wanted to figure out how much did you start off with of this radioactive isotope before it started to decay. So what if you wanted to calculate the half-life of technetium-99 is 6 hours? If 10 micrograms are left after 24 hours, how much was administered to the patient originally? So we need to figure out how many half-lives went by in 24 hours. So that's the first thing we need to do. So we would take 24 divided by 6, and we would see that there are 4 half-lives that went by in the 24 hours. So now what we're going to do is we're going to start with our ending mass, and instead of halving, we are going to double your amount, the number of half-lives you calculated. So this is how we're working backwards. So our ending mass was 10, and we have to double it 4 times. So that means that we need to multiply it by 2 4 times. So when we do that, we do 10 divided by 2, that answer times 2, that answer times 2, that answer times 2, and we get 160 micrograms. So the patient was administered 160 micrograms at the beginning of the 24-hour period. What if you were asked to figure out how much time elapsed? This is another type of question that I can ask you. First, you would look at how long it takes for a 400-gram sample of phosphorus 32 to decay to 50 grams. This again is a two-step problem. The first thing you need to do is you need to find the number of half-lives that passed by dividing the original mass in half until you get your final mass. So we started off with 400 grams, and I wanted to see how many times I would have to cut it in half to get to 50. So 400 divided by 2 is 200. 200 divided by 2 is 100. And 100 divided by 2 is 50. So that means that I needed to cut this in half 3 times, which means 3 half-lives have gone by. Now what you would do is I want to know how long it would take for 3 half-lives to go by. When you look up in table N, you will see that there are numbers of half-lives like we've said before, but that is for 1 half-life. We've just calculated that 3 half-lives have gone by. So if you take the amount of time that it has for 1 half-life times 3, because 3 half-lives have gone by for 400 to change to 50, you would get a total time has passed of 42.9 days. So let's look at a practice problem. We just went through all of the types of example problems that I could go through with you and ask you in your practice packet on a quiz or on a test or any other assessment that I'm going to give you. So, what mass of a 100-gram sample of carbon-14 will remain after approximately 23,000 years? So, figure out what kind of problem this is, look back in your notes, and see if you can solve this on your own. Great, what did you come up with? You should have figured out that this is an amount remaining problem, and so you would use that part of your notes to help you figure this out. So the first thing you're going to want to do is, this is a two-step problem. You're going to want to figure out how long is 1 half-life of carbon-14. 1 half-life of carbon-14 is 5,730 years. The next thing you're going to want to do is you're going to want to calculate the number of half-lives that have passed in 23,000 years. So you're going to take your 23,000 years divided by 5,730 years, and you're going to understand and see that 4 half-lives have gone by. So now what you're going to do is you're going to take your 100-gram sample and divide it in half 4 times. When you divide it in half 4 times, your final mass will be 6.25 grams, and that's how much will remain. Let's look at another practice. This one says, if 1.25 grams of iodine-131 remains after 40 days, what was the mass of the original sample? Pause the video and unpause this when you're ready. Great, well, what did you come up with? Remember, the first thing you should have done when you read through this question is figured out what kind of problem is this. This is a calculating of the original mass. So those are the notes that you should have followed in order to answer this question. So the first thing we need to do is find out what the half-life is of iodine-131. We know that the half-life of iodine-131 is 8.07 days. So to figure out how many half-lives have gone by in the 40 days, we are going to take 40.4 divided by 8.07, and that shows us that we need to double our 1.25 grams 5 times, because remember, we're working backwards in this problem. So we're going to take 1.25 and we're going to double it 5 times, and when we do that, the mass of our original sample would be 40.0 grams. Let's look at one final practice problem. Now, this practice problem says, how many half-lives will U-238 go through in 2.255 times 10 to the 9th years? Pause the video, try this on your own, and unpause when you're ready. Well, what did you come up with? Well, this is a determining the number of half-lives problem, so you should have followed those notes when you were going through this practice. The first thing you need to do is find out what the half-life of uranium-238 is. And the half-life of uranium-238 is 4.51 times 10 to the 9th years. So now you need to figure out how many half-lives went by. So you would take your amount of time, the 2.25 times 10 to the 9th years, divided it by how much 1 half-life is, and you would have figured out that that is half of a half-life. So now that we've done a couple examples on your own in your practice, let's see if you can try this, check your understanding, and we'll go over this first thing in class tomorrow. Have a good day.